Okay, part 4. Let's see if to start off we can lay the groundwork. We're going to do a couple things. We're going to try to show the basis, the theoretical basis of where the 30, 60, 90 special right triangle comes from. Also, where the 45, 45, 90 right triangle comes from. It's all going to be based on this idea of a unit circle. So, a unit circle is when we're putting our reference angles onto a coordinate grid. It's also basing on the special points of 1, comma 0, 0, comma 1. Basically, any circle with radius 1, negative 1, comma 0, and 0, negative 1. So from there, here's how I'm going to approach this bad boy. I'm going to want to make a reference angle, so an initial side out to 1, comma 0, and a reference angle of 60 degrees, right? That means our remaining, this has to be 30 degrees. And there's some other things I can write in here. We'll call this 1 because from 0, 0 to 1, 0 is 1. We'll call this x because we don't know yet, and we'll call this y. So the first thing I'm going to do is a simple trig problem that goes cosine of 60. So cosine of a reference angle is adjacent over hypotenuse. So adjacent over hypotenuse. If your calculator's in degrees and you take cosine of 60, you get 1/2 equals 1 over x. Multiply both sides by x. Divide by 1/2. So now we can say that our hypotenuse of this reference triangle is 2. Right? From there, I'm just going to use a Pythagorean theorem, a squared, b squared, c squared. So 1 squared plus y squared should equal 2 squared. 1 plus y squared equals 4. Subtract the 1 over 3. Y equals the square root of 3. Really plus or minus, but since it's a distance, we won't. So what you're seeing then is this is where the 30, 60, 90 triangle comes from. All right. Just throwing that out there. So let's try to repeat the process. Let's try to repeat the process with the 45, 45, 90 triangle. So again, coming out to 1, 0. We'll just stay in the first quadrant. Easier, better that way. Initial side, we're going to try to make a reference angle of 45. Throw us a right angle in there, 45. So this one actually ends up getting easier, right? By definition, this triangle is isosceles. See if I can spell this right. Isosceles triangles have two sides that are congruent, right? And two base angles that are congruent. So the fact that we have a 45 and a 45 tells me it's isosceles. So if this side is 1, then I know this side can also be 1 by definition of isosceles. So then the only thing I got to do is solve for the hypotenuse. And it's easiest to just use the Pythagorean theorem. So then I got 2, 1 squared, 1 plus 1 is 2, x squared, square root of 2 equals x. So we're going to go ahead and show that this is square root of 2. I'm not sure that you'll get a straight up test question on deriving these things. It could be bonus, we'll see. This next part is going to be my quick justification of what you see in this textbook chart, and then we'll talk about a quick and dirty way to memorize that. All right, so let's say in general we make a reference angle in quadrant 1. Whatever point we put out here, all right, it's going to be a positive x and a positive y, right? So what that does is tell me that the height here is going to be positive and this is going to reference positive. When we do a like Pythagorean theorem of some positive number, if you want to plug in a positive number there, but positive squared plus positive squared, and we're trying to find the hypotenuse squared. Again, we put these two together, right? We'll call it 2 positive squared, as weird as this is, equals hypotenuse squared. When we square root it, the big takeaway is that the hypotenuse will also be positive. So now, if you would use SOHCAHTOA, right? Sine of some reference angle will be opposite over hypotenuse, positive over positive, every single time. If we do cosine of sigma of our reference angle adjacent over hypotenuse is positive over positive, which means it's going to come out positive. Tan of theta, opposite over adjacent, positive over positive, and that's going to come out positive. That's what you're seeing right here. And really, this is all going to apply to section number 4. But the biggest thing is to recognize this in quadrant 1. We'll make this way more applicable down below. But now let's work through the other 3 quadrants. Let's get rid of some of this so we have more room. So now let's go into quadrant 2 and see if you can hang with my abstractness here. If we put a point here, we have now gone into the negative territory on x, and we're on the positive side on y. We are climbing up the y-axis in a positive manner, but we're going negative x in that manner. So now we draw in a reference, sigma. Let's think about a few things, right? So if we're going back x, technically we're going negative here, we're going up here. If we would do a Pythagorean theorem, negative squared plus positive squared, that's going to come out positive, that's going to come out positive, so our hypotenuse is also going to be positive. Now, if we go into our trigs of SOHCAHTOA, we go sine, cosine, and tangent. If we go opposite over hypotenuse, we're going to get positive. If we go adjacent over hypotenuse, so this is the first time negative divided by a positive comes out negative. And if we go opposite over adjacent for TOA, we're going to get opposite over adjacent, which is also going to come out negative. So you'll notice that the only thing that is positive here is sine, right? And I should also say in both sections that like sine and cosecant follow the same properties. Cosine and secant follow the same properties. Tan and cotan are paired together. So what I'm trying to establish here is that in quadrant 2, only sine, and really this is the technical way to spell sine, is positive. So let's follow along that same discourse and see this about quadrant 3. So now if we put a point here, now we're in the negative x because we're going left, and we're in negative y. So when we draw in a reference triangle, we went back on this side, we went down on this side. The one thing we will see, negative squared, some negative numbers squared. If for the hypotenuse squared. Negative squared is positive, plus negative squared will come out positive. So our hypotenuse will always be positive by the time we square everything. But now we start thinking sine. I hate when it does that. Cosine and tangent. Opposite of the reference angle to the hypotenuse. Negative over positive, which will come out negative. Cosine adjacent over hypotenuse will also come out negative, but tangent opposite over adjacent, negative over a negative, will come out positive. So our note there is in quadrant 3, the only thing positive is tangent. Fourth and final, if we go over here, we are now in the positive x-axis, still in the negative y. We're drawing a reference angle. We are now at a positive and a negative, and the hypotenuse will come out positive. You can verify using trig. If we go sine of sigma, cosine of sigma, tangent of sigma, and we go opposite of the reference angle over the hypotenuse, it comes out negative. If we go adjacent over hypotenuse for cosine, it comes out positive. And if we go opposite of sigma over adjacent, it comes out negative. So the big thing to focus on here is the only thing positive in the fourth quadrant is cosine. So all that being said, to wrap up this little section is this. In the next section, you're going to be asked to evaluate functions without a calculator. And it's going to put a lot of the last two videos together. You're going to have to draw a correct reference angle, a correct triangle, but then we're also going to use trig ratios, and then we're going to have to reference whether it should come out positive or negative by this chart. To memorize this thing, here's what I was taught way back in the day, right? Everything is positive in this quadrant. Only sine's positive here, only tan is positive here, only cosine is positive here. The way my old math teacher, shout out to Mr. Stewart, taught me this to memorize this was all seniors turn crazy. So it's a memory mnemonic to try to remember which quadrants are positive. All right, I'll see you in the next video.